Hello there, welcome to this video 6-10, and today we're going to talk about u-substitution in calculus. One of the most difficult and complicated topics in calculus AB. Now before we go ahead and dive into that, I did want to go over how to find all of my videos on my website so that you can see the videos in an organized manner. If you Google Schwarberg Math, my last name followed by math, you can find my website here. It's just a Google Sites, Schwarberg Math, and you'll see I have my 3 courses that I teach: Math 3, Accelerated Math 3, and Calc AB. Now the units are organized by lesson, so you can easily see lesson 1, lesson 2, lesson 3 in that order, okay? So hop on over to the website, check it out. All right, our learning intention today, we want to learn how to utilize u-substitution while integrating symbolic functions or executing antiderivatives. Now here are the 5 antiderivatives or integration rules that you must know stone cold. So just a recap, we've talked about these lots of time, and notice each of these integration rules above, they use the variable u along with du instead of x and dx. Now why are we doing that? Well, this is because of the problems that we encounter on the AP exam. They're rarely just simply or involve just a plain old x, the basic antiderivatives that we've been working with. They are a little bit more complex. So we're going to go ahead and develop this idea of how and why do I utilize u-substitution. So I want to go ahead and look at this basic example here. The integral of cosine of x dx is equal to sine of x plus c. We know this, right? This is a basic antiderivative. I take the derivative of sine of x plus c and we get cosine of x. But the integral of cosine of 2x dx does not equal sine of 2x plus c. And maybe you're asking yourself, why? Or maybe I'm asking you, why? Well, if I take the derivative, d dx, of sine of 2x, I'll even throw in the constant, could be any value. We know that the derivative of sine is cosine, so I have cosine of 2x, but I have a function within sine of x. And the derivative of that, if I multiply by this, right, this is just the chain rule, is times 2. So notice that the antiderivative, we have to deal with this chain here, okay? So this concept is pretty much the same idea as using the chain rule for derivatives. Okay, and in order, when I have a function within another function, right, I have that 2x inside of cosine, we have to go ahead, when using antiderivatives, we have to use what's called u-substitution. Okay, now the most important piece to this is identifying the correct u. You got to identify the correct u. Now, what is u? Well, Brian Passwater likes to call it junk. The junk in the trunk. Find the junk. And the junk is usually, sometimes not always, it's the stuff in the parentheses. Okay? The junk usually is more complicated. Expression that takes the place of where normally just a simple x would make it look so much pretty, right? So it's very, very ugly, just like maybe you before you put on makeup, right? Very ugly, you put on makeup, oh, it's nice, okay? The u, what we're going to do when we substitute, is like the makeup, okay? So identifying that u. Now, there are a couple of other ways just in the parentheses to identify u. We'll talk about them here. Here are the strategies or just the general approach and procedures for u-substitution. Step 1, identify u. And what you're going to do is you're going to set an expression equal to u. Look for parentheses or radicals or exponents. I'm going to add this one in here too. Radicals or exponents. Step number 2, find du. Now this is just done by differentiating both sides of your u equation. Very simple. Step 3, we'll substitute into the original problem. 4 will fix any constants that need to make the du work. Okay, I'll elaborate more on this. Step 5, integrate one of using the 5 antiderivative formulas above. And then last but not least, we'll substitute back into the expression for x, okay? And this is only for indefinite integrals. We'll get to definite integrals later on in this video or in a secondary video. So let's go ahead. Let's see what all the fuss is about. Here is example number 1. The integral of 2 sine of 2x dx. I can't integrate this as is because I have a function within another function. So what I'm going to have to do is I'm going to have to go ahead and identify u. U is right here. That's that 2x. U is equal to 2x. Now, what I have to do is I have to go ahead and identify du. I have to identify du. And that's just the derivative of u. And then the derivative of the other side of 2x is just going to be 2 times the derivative of x, which is dx. So I'm going to make this swap, and you'll see why when I make this swap, how it's so much easier to take the antiderivative. But what I'm going to do is I need to replace these items. I've already underlined 2x. You can see 2x here. Now I'm going to underline 2. I have to have these items to substitute in du. So I have to have a 2 and I have to have a dx. Now one thing I do like to do is I do like to organize my integral with the du at the back. So you can clearly see here, here's the u, here's the du, and this just makes the swap so much easier for my students to see. So now I have the integral of the sine of u du. Okay? And with that swap, hey, isn't this one of the basic antiderivatives that we had talked about? Sure is, and the antiderivative is negative cosine of u plus a constant, right? This is an indefinite integral, no limits of integration, so I add that constant. And now I'm going to make the swap. I'm going to go back to terms of x. So negative cosine of 2x plus c. I just put back instead of u, put it back as 2x. There's my answer. Don't box. Do not box it. Don't box your answer. On the AP tests, on FRQs, do not box. Just leave it like that. Now, one thing that's cool with calculus, right? Integrals and derivatives, they're inverses. I can check my work. If I wanted to say, hey, am I right? I can take the derivative of this, right? What's the derivative of negative cosine of 2x plus a constant? Does it give me my integrand, 2 sine of 2x? It sure does, okay? So that's u substitution. Let's go ahead and look at it in example number 2. The integral of x squared over the square root of x cubed plus 1 dx. Now again, step number 1, identifying that u is the most complicated part. You'll get pretty good at this. You'll see, okay, what can I do to make this substitution? Here's some tips. Whatever your integrand, or sorry, your radicand is, that's generally what your u is going to be. So my u here is x cubed plus 1. And then my du, the derivative of this, is going to be 3x squared dx. 3x squared dx. Okay, so let me go ahead and just kind of rearrange this so that you guys can clearly see the square root of x cubed plus 1. Back here I have x squared dx. And what I hope you see is that I'm just missing, right? I'm missing the 3. I don't have that 3. I have to introduce this. I'm going to multiply it in. Now, you guys should know you can't just add whatever you want to an equation, but really I'm going to multiply by 1. Multiply by 1 by 3 over 3. And I'm just going to multiply by 1/3 on the outside of the integral, right? So really I'm multiplying in 3 over 3, which is just 1. I'm not changing this. I'm just kind of, balancing this equation. Multiplying by 3, dividing by 3. I didn't do anything to it. Okay, but what this allows me to do is now I have the du, and you have to have that du. So when I make this swap, we now have 1/3 times the integral of, we have u to the power of -1/2. I hope you see I just changed this to a power 1/2 and brought it up with the negative exponent property. And then 3x squared dx, that's du. That's du. So when I make this integration, I have 1/3 times the integral of u. I'm going to raise that power by 1. This is just basic power rule. I'm going to add 1, and I'm going to divide by my new power, divide by 1/2, which is the same thing as multiplying by 2 over 1. Okay? Plus a constant. Plus a constant in here. Plus that constant. Okay? And let's go ahead and just kind of clean this up. So we have 2/3 times the square root of, and I'm going to go back to x cubed. So x cubed plus 1 plus c. And there is your answer. Don't box it though. Don't box it. Man, I tell my students this, and then I do this all the time in the class. I box my answer. We're so used to doing that in math. I'm not going to box it. On the AP test, don't box it. Don't box your answer. Okay, example number 3. The integral of x e to the power of x squared minus 1 dx. All right, I told you it's usually, the u is usually in parentheses or in radicands or exponents. This looks so nasty because I have a function up here in the exponent. Well, if I just say, hey, x squared minus 1, that's my u, this becomes so much cleaner, and I'll show you here in a second. The derivative of this is 2x dx. Now notice, I have my dx, I have my x, I'm missing the 2. So what I'm going to go ahead and do is I'm going to multiply in the 2. So here I have e to the power of x squared minus 1, that's my u. I have this x back here, I have a dx, I'm missing a 2, so I'm going to balance it with a 1/2. If you add it in, if you multiply it in, you have to balance that factor with a 1/2. Okay, now let's make that u substitution swap. So this is 1/2 times the integral of e to the power of u, and all of this is my du. Hey! This is the best. This is the Spider-Man meme. E to the u is e to the u. I love it. I love it. So I'm going to go ahead and integrate this. We get 1/2 e to the u plus a constant, okay, which just gives us 1/2 e to the power of x squared minus 1 plus a constant. There it is. U substitution's easy. It's easy, man. All right, example 4. Example 4, the integral of 3 over 4 minus 2x. All right, well, here I have a variable. This whole term here, 4 minus 2x. 4 minus 2x. I have 2 terms here in my denominator. So that makes this complicated. One strategy is if you have a power of 1 in your denominator, just make your denominator equal to u. I'm going to make u 4 minus 2x. The derivative of this, du, is going to be equal to -2 du. All right, so what do I do with that 3? I have a 3. I don't have a 2, I have a 3. Well, there's no way to turn that 3 into a 2. So what I'm going to do, I'm going to pull that 3 out into the front. And I am going to go ahead, and this will be my u, right? 4 minus 2x. And we'll move the d, that should be dx, not du. Move the dx back here, and I'm missing my -2. So I'm going to add in a -2, and I'm going to balance that with a -1/2. With a -1/2, right? -1/2 times 3 gives you the -3 over 2. Okay, so there is my set up, and now I'm going to go ahead and make this swap. So negative 3/2, the integral of 1 over u, that's just u to the negative first, du, okay, and the integral of u to the negative first. If you're thinking power rule, that negative 1 becomes a 0, and you divide by 0, which is not allowed. We know this. The world will explode. So this rule, right, this is 1 over u, which we know is the natural logarithm of u, which is, in this case, 4 minus 2x, plus a constant. Okay, and there's your u substitution. So easy, so easy. Example 5. Okay, this one, the u substitution. I love the discussion on this, and this happened organically in my class. One of my students said, okay, I think u is 5 plus 3x to the power of 2. I'm going to make the whole denominator u. Okay, that would set us up good to be like the last example where I have 1 over u. The derivative of this, and this is the problem. If you're writing this down, don't write this down. I want you to stop right here. I just want you to watch because this is not u. The du would be, what's the derivative of this? Well, I have power rule first. I have 2 times 5 plus 3x times the derivative of the inside, which is 3, which is 6 times 5 plus 3x. And obviously I could go ahead and distribute this. Moral of the story is I don't have any other x's or any other variables, or I don't have anything that looks like this in my integrand. Now, I've taught you that you can multiply in constants, but I cannot multiply in and generate variables. I cannot do that. So this, if you ever get to this, you're like, I don't know what my u is, like I'm scared. Well, don't be paralyzed by fear. Take a step. Right here, I realize I'm in the thick of it. I'm like, oh no, this is pretty scary. I'm gonna get out of here. I'm gonna erase this or put a line through it, right? If it's my AP test, and I'm just gonna reevaluate my u. I'm gonna let my u. Don't be afraid of the powers. The powers are fine. We have the power rule, right? As an antiderivative process. I'm going to let the stuff in the parentheses be the u, and then the du is going to be equal to 3 dx. Let me put this in blue to keep my nice color organization going. 3 dx. Okay, so this becomes negative 4 times the integral of 1 over, we have 5 plus 3x to the power of 2 in the denominator. Now I'm missing my 3, so I'm going to go ahead and add in the 3. And I will balance it with a 1/3. Okay? So if you introduce a variable, you better balance it. Okay, so now I can make my u substitution. We have negative 4/3 of the integral of u to the power of negative 2 du. Okay, which this is just simple power rule, negative 4/3 u to the power of negative 1. So 5 plus 3x to the power of negative 1 plus a constant, and we're going to divide by the new power. Divide by negative 1. I'm just going to divide all this by negative 1. You agree a negative times a negative is a negative. So we get a positive 4/3 times 1 over 5 plus 3x to the first power, which is just that, plus a constant. So this equals 4 over 15 plus 9x. Plus a constant. I just distributed that in, and there you go. Do I have to go that far? Well, it depends on what you're doing. If this is just FRQ, which I doubt you would never get an FRQ question. I don't believe that would just say, find the antiderivative of this, right? You'd most likely have to be doing something with this to get an answer. So you're going to evaluate. It will become a definite integral, which we'll look at. Or this is a multiple choice question, which they'll probably make you go this far. Okay? So keep those algebra skills sharp. Example 6. This is the last example that I have, and I'm going to have you try this, but I'm going to have you try this. But first, I just want to demonstrate again, I want to remind you of this property of integration. I have the integral of sine of 3x minus cosine of x dx. We'll get to u-substitution involving trig functions, but not right now. I just want to remind you, if you are adding or subtracting terms, you can represent this as multiple integrals. This is the integral of sine of 3x dx minus the integral of cosine of x dx. Okay, so I want you to go ahead, please pause me, please try this. I want you to integrate. I'll unpause and I'll show you the answer here in a moment. Okay, awesome. Hopefully you went ahead and tried this one. This integral right here requires u substitution. U is equal to 3x, and then therefore du is going to be equal to 3 dx. So we have the dx. I'm missing a 3, so I'm going to have to add in the 3 and balance with the 1/3. And then here the integral of cosine, that's just a regular old antiderivative. So let's go ahead and integrate this. This is 1/3 the integral of sine of u du minus the integral of cosine of x dx. Woo, this is a little weird. I feel weird working with x's and dx's. But you get negative 1/3 cosine of u, which is 3x. Okay, minus the integral of cosine of x, that's just sine of x. And I do have one constant, okay? So that's going to do it for this video. That is u-substitution in a nutshell. The next video will focus on u-substitution utilizing definite integrals. Like and subscribe. I'll catch you in the next video. Keep it real.